In this video, we will discuss what is considered to be important kinetics information for your kinetics test in AP Chemistry. Now, of course, we're not going to be able to cover everything that is just going to be on the test, but chances are if it's in here, it's probably going to show up on the test in some form or another. So how I would like you to work through this is that you'll pause the video, you'll answer these questions, and then you can resume the video and check your answers, okay? It's important that you are following along and you're actually writing this out because, of course, on the test, that's what you'll have to do. Okay, so what must happen for a reaction to occur? Well, let's make up a reaction and we can say A plus B forms, let's say, C. And so what I know is that A and B have to collide. But with their collision, most of the time they're just going to bounce off of each other. And so they have to have the correct orientation. And they have to have the right energy. And that would be enough to reach the activation energy. Okay, what else is also important is let's write a rate law, and we could say rate equals K for this reaction. I'm just going to make this up. If this is the overall reaction, I have no way of figuring out the rate law without giving some experimental information. So I'll just say A to the first power, B to the second power. And what those powers mean, those are the orders. And what those mean is that if this reaction were to occur in one step, it would take one A molecule and two B molecules to collide at the right orientation and the right energy. That would be very unlikely. But we could also have a rate law. Let's compare it to rate equals K. Let's say A is to the first power, and then B is to the 0 power. So what that would mean is that it wouldn't matter how much B there was. This rate is only dependent on A. So maybe A has to break in half first, and then it can react with B. So it doesn't matter how much B you have if that's the situation. Okay, let's talk about a catalyst. Catalyst, a lot of people know, is that they speed up a reaction. And the important thing is they speed up a reaction by lowering the activation energy. And catalysts are not consumed. And what they will do is that, let's say we have molecule A and molecule B. Let's say in order for those two to react, there's this small sliver of A that has to touch this small sliver of B, whatever A and B are. What a catalyst will do is a catalyst will make sure the two parts that need to touch, the orientation is just perfect, and they will slam them together to get them to react. Okay, Boltzmann distribution curves. These are common in AP Chemistry, and here's what you want to know about them is that, let's say I've got an area here, and then I'm going to stop it right at the activation energy line. And what this represents is this is the particles that do not have enough energy to react. And then I could also look at these molecules here, and these do have enough energy. Okay, so it's important you know how to read this graph. And then let's say I lowered the temperature. Well, if I lower the temperature, I'm going to be essentially removing heat or energy from my system. And so the amount that can react, that's probably going to be a little bit lower. So maybe it's just this much, and I'll draw what that might look like for a curve. So maybe something like that. And then the amount that don't have enough energy, that would be way more. So maybe it looks something like this. And then I can draw my curve. So something like this would be at a lower temp. Okay, now, what if I ask a question, if I got another Boltzmann distribution here, what if the temperature is the same? If the temp is the same, that means the curve is the same. I didn't add any energy if the temperature is the same. But let's say I still sped up the reaction. That would mean I most likely had a catalyst. So let's see what happens if I added a catalyst and then the temperature is the same at the same temp. Okay, my curve needs to be the same, and so I still have the same curve here. But catalysts, we've already talked about, they lower the activation energy, so this dashed line, that's my activation energy. I need to move that somewhere maybe over here, and so that basically gets lowered. And what that means now is that instead of just this amount of particles that can react, I now have a larger chunk of my graph, and those particles can react. Okay, let's look at relative reaction rates, and I kind of think of these as just mole bridges. So what we have going on is we have a reaction. We have ammonia plus oxygen gas produces NO2 gas and water gas. And what I know is I know that water is being formed at 36 moles divided by liters per minute, which is 36 moles over liters per minute, or we might see it 36 molarity per minute. Oftentimes we will see minutes, but or oftentimes we'll see seconds, but it's not uncommon completely to see minutes. And so if I want to know about ammonia, all I'm going to do is just mole bridge. So I'm going to say, okay, I've got 36 moles of, that's water, H2O, for every liter per minute. And I'm going to say, okay, moles of H2O to moles of ammonia, and that's NH3. And when I do that, there are 6 moles of water, 4 moles of NH3, and so I will get 24 moles divided by liters divided by minutes, or 24 molarity per minute, because moles and liters combine to be molarity. But what might end up happening on the AP test is that this could end up being negative. And the reason why it could be negative, so you're not wrong if you say 24 molarity per minute if you say used. Or it might be represented negative 24 molarity per minute, and the negative is saying that, okay, well, NH3 is a reactant, and so it's going to get used, and so that's what the negative means, is that it's decreasing. Or if I graphed it, and we've done graphs before, the NH3 would be something like this maybe, where it's decreasing over time. Okay, let's look at letter B. We are asked to solve for nitrogen dioxide. So what I'm going to do is I'm going to set it up exactly the same way. And I'm just going to change what's going to be different. And it's just up there in my dimensional analysis fence. And nitrogen dioxide is also 4. So 4 moles of NO2. And so I get 24 moles divided by liters per minute, or 24 molarity per minute. And this one will be positive always because it's being produced, and so sometimes it might have a positive sign out in front. The positive sign or the negative sign is just showing you what side of the reaction your compound is on. Okay, now let's look at rate laws. This one is pretty easy in A, so you can fast forward if you want to letter B. Letter B is a very good one, but we'll get there. On this one, we're asked to solve for the rate law and the rate law constant. And if this is a free response question, it's very common for people to forget to solve for K. So if you remember, what we want to do is we'll call this X for NO and BR2 will be Y. And I know that my rate law is going to be something to the effect of rate equals K, NO to the X power, BR2 to the Y power. And I just need to solve for X and Y. And if I want to solve for X, I need Y to drop out. And so I see in experiments 1 and 2, I can get Y to drop out. And I'm going to choose experiment 2 to be my numerator just because it has a larger rate. That's 150 molarity per second. That equals K, 0.25 to the X power, 0.20 to the Y power. And I'm going to divide all that by rate 1. That equals 24 molarity per second, which equals K, 0.10 to the X power, 0.20 to the Y power. And so I get Y to cancel and K to cancel. 0.25 divided by 0.1 is 2.5 to the X power. 150 divided by 24 is 6.25. And depending on your proficiency with natural logs, this might not be a difficult question, but they are decimals. So what I would recommend doing is you can plug in 1 for X, and obviously that won't be the power, and just keep going. Now move on to 2 and see if 2 gives you the right answer, and if it does, then great, you're done. If it doesn't, try 3. It's a lot easier when they are whole numbers, but actually 2 works out, and so the power of X is 2. And then now what we're going to do is we're going to try to find an experiment or 2 experiments where X will drop out, but Y will not. And we could do 3 and 1, and that actually looks like what we have to do. That's the only one that'll work. And again, I'm going to put rate 3 on top because it's a larger number. And so I'll do rate 3 equals 60 molarity per second, which equals K, 0.10 for X. But now that I know X and that it's 2, I'm not going to plug in X. I'll just plug in 2. And then 0.50 to the Y power. I'll divide that by rate 1, which is what I had just here. And when I look at this, my NO cancels and my K's cancel. So I'm left with 0.5 divided by 0.2, and that is 2.5 to the Y power. 60 divided by 24 is about 2.5, and so Y is equal to 1. So what I can do is I can go back to my rate, my generic rate law that I had at the beginning here, and erase X and erase Y. Plug in 2 and plug in 1. And now to solve for K, that's the last thing I need to do. Remember, to solve for K, you just pick an experiment. And so what I'm going to do is I'm going to use experiment 1. I tend to use experiment 1 for all of these, and I'm going to just plug in the numbers that I know. My rate is 24 molarity per second. That equals K, 0.10 squared times 0.20 to the first. And what I need to do is I need to isolate K. So I'll multiply these two guys and then divide them over. And what I end up getting, let me just double check, 0.1 squared times 0.2. 24 divided by that. I get 1.2 times 10 to the 4th. And that equals K. But on the test and on the AP test, you have to put units. You never ever get points for K unless they have units. So later in the video, we'll talk about what those units will be, but it's molarity minus 2, seconds minus 1. We will always have a time minus 1 unit. Okay, Letter B. Letter B is an excellent question. And so what I'm going to do is I'm going to solve it the same way, x and y, and I can use experiments 1 and 2 to get y to cancel. And I know my generic answer is going to look like S208 to the x power, and then I minus to the y power. So I'm solving for x first, and I'm going to put rate 2 on top. Rate 2 equals 3.9 times 10 to the minus 6, which equals k, 0.027 to the x power, 0.036 to the y power. Then I'm going to divide that by rate 1, which equals 2.6 times 10 to the minus 6. And I should really, and I'm going to do that just to make sure my work is as good as it can be. This should be molarity per second. My y's cancel, my k's cancel. 0.027 divided by 0.018 is 1.5, and that's to the x power. 3.9 divided by 2.6 is also 1.5, and so x equals 1. Now here's why I put this question on here. There is no way to get x to cancel, because all my x's, or my S208, those are all different. So what I want to do is I just need to pick 2 experiments where y doesn't cancel. And so I've picked 2 and 3, but you could pick pretty much anything except 1 and 2. And between 3 and 2, rate 3 is the largest, so I'll have that be my numerator. And that equals k, 0.036 to the x power, but x is 1. We just solved for that. 0.054 to the y power. We are solving for that. And then I will divide it by rate 2. And within rate 2, nothing cancels except my k's. So what I'm left with is 7.8 divided by 3.9, and that is 2. 0.036 divided by 0.027, that's right here. That is 1.33. And then 0.054 divided by 0.036, that's going to be 1.5 to the y power. I'll divide each side by 1.33. 2 divided by 1.33 is approximately 1.5, and that equals 1.5 to the y power, so y is equal to 1. Okay, so now I've done the hard work, and that's the only way that this problem is different. Now, all you have to do is solve for k, so go ahead and practice that. And they're both 1. I'm going to use experiment 1. And we get 2.6 times 10 to the minus 6 equals k. 0.018 to the first power, 0.036 to the first power. And I got k to be 4 times 10 to the minus third. We are overall second order. And so what that means is my units on this will be, we always will have seconds to the minus 1 and then molarity minus 1. Okay, so let's talk about the rate constant, because that's a huge thing in this unit, and that is just k. And what is important to know is that your exponents should add up to the overall order of your reaction. So let's say I had an overall order of 2. I'm always going to have per second, or seconds to the minus 1 power. And right now, if I added that, I only have 1. So what that means is I need a molarity to the minus 1 power. And so you can see that 1 and 1 will equal 2. And that's exactly what we had up here. Okay, that's the units that we got. Now, let's say I gave you an overall fourth order. That's still a common one. The seconds will stay the same. All I have to change is the molarity, and the molarity to get it to add up to 4 would be -3. This trick will help you out when you have an overall order. Let's make it 54, which that's very, very, very unlikely. But my seconds is always to the -1 power, or it could be minutes to the -1 power. So what this would be is -53 to get it to add up to be 54. If I see a graph like this where I have two different graphs, it must be first order because the natural log plot gave you a straight line. But between W and Z, W must be a faster reaction because they both started here, but W finished faster or in less time. So W must have a higher rate constant. Okay, or you could say that it was at a higher temperature because increasing the temperature will generally increase your rate of your reaction. And the only thing that changes rate constant, and I would know this, is temperature. And it's going to be a direct relationship, so higher temp will equal higher K. Okay, integrated rate law, I'm going to touch on this. This is where people, if they're going to mess up, this is likely where they'll mess up. We remember our trick from our AP formula sheet 1 to 1, and the only half-life we are given is for a first order process, but we can use our second order integrated rate law for half-life, and I think I have an example in here. But here's what's important, is when do you use these formulas? Only when you are given time information. Okay, that's the only time you're going to use your integrated rate law. So please, please, please do not overuse them. With the integrated rate laws, sometimes you'll see graphs and concentration versus time. If it produces a straight line, it'll be zero order. If you graph ln concentration versus time and it gives you a straight line, it'll be first order. And if you graph 1 divided by concentration and versus time and it gives you a straight line, it'll be second order. And I would write down that the absolute value of the slope is equal to K. Okay? So let's look at A. It says the decomposition of ammonia to nitrogen and hydrogen is a first order reaction with a half-life of 200 seconds. Okay, they're mentioning time, so that makes me think I need to use the integrated rate law. They tell me that it's first order, so that's important. I want to know ultimately how long it will take for the pressure to decrease from 0.1 to 0.00625. Okay, so what I know is that it's first order, so I'm going to write the first order integrated rate law. And the initial pressure, which we can plug in pressure instead of molarity here, is 0.100 ATMs. And then it's 0.00625 ATMs. We're not given K, but we're asked to solve for time. How long will it take? So I must have to solve for K here, and I'm going to put parentheses, and then time is what I'll ultimately solve for. And what you may notice is that I haven't used the half-life yet. So there's another formula, T1/2 equals 0.693 divided by K. And so what I can do is I can erase the half-life because they tell us that it's 200 seconds. So when I math that out, I get 3.465 times 10 to the minus third, and that's seconds to the minus 1 power. So what I'm going to do is I'm going to take that and I'm just going to put it in here, and I'm going to do this math. Okay, so make sure you can do this. We'll take the natural log of 0.00625 minus the natural log of 0.1, and then divided by, don't forget the negative, 3.465 times 10 to the minus third. And what I get for t is I get 800 seconds. Okay, that's how long that'll take. If I look at letter B, it says we have a chemical reaction. It's a decomposition. We're at a temperature. The concentration versus time data was collected, and they graphed 1 divided by concentration, and that resulted in a straight line. Okay, that's going to be important. We have a slope of 0.00378, and I've made a typo. That should be molarity minus 1, seconds minus 1. So I will fix that on yours. And we are asked to solve for the time that it would take for A to decrease. So here's what I know, is whenever they're talking about a straight line, I need to think back to this picture. And they graphed 1 divided by concentration versus time, and that gave me a straight line, so that must be second order. But if you don't know, just look at your integrated rate laws. The only ones where they'd take 1 divided by A would be second order. So we can put that in here, 1 divided by A sub t minus 1 divided by A sub 0 equals kt. And the concentration after some amount of time was 0.294. The initial was 1.25. This absolute value of the slope, which this one's positive, so we don't have to worry about that, but it's 0.00378, and that represents our rate constant. And then on this one, we're solving for time again, so we just have to do a little bit of algebra. 1 divided by 0.294 minus 1 divided by 1.25, and then divide that number by 0.00378, and we get 688 seconds. Okay, letter C is a good one because this one requires you to manipulate a first order rate law when solve for a variable that's within the natural log. Okay, so we are given this reaction, and our rate constant is 4.5 times 10 to the minus 2. The only reason they give us a temperature is because that's the only time that this number, the rate constant number, is true. And we start with a concentration of 6.25 molar. We want to know the molarity after 60 seconds. Okay, so we can say ln A sub t minus ln A sub 0, which is the initial, equals negative kt. We are solving for the concentration of A, which in this case will be SO2Cl2. The initial was 6.25 molar. K is 4.5 times 10 to the minus 2 seconds to the minus 1 power, and just a minute passes, which is 60 seconds. And so what I'm going to do is I'm going to multiply these two guys. I get negative 4.5 times 10 to the minus 2 times 60, and I get negative 2.7 equals this. What a lot of people will do is they will divide, but what you need to do is add over the natural log of 6.25. And so I'm going to do that in my calculator. And what I get is I get negative 8.1 oh, I'm looking at that wrong, close, negative 0.867 equals ln SO2Cl2. And the way you get rid of a variable within a natural log is you take e to whatever number is on the opposite side. So e to the negative 0.867 will equal the concentration of SO2Cl2. And so e is to the negative 0.867. And what I got is that the concentration of SO2Cl2 is 0.420 molar. So this must be a very quick reaction because we start with such a large concentration and only after a minute it's so much smaller. Okay, the last topic we'll cover is reaction mechanisms. So if I wanted to get the overall balanced reaction, what I'm going to do is I'm going to look for things that will cancel. Okay, and so the things that cancel, that's going to be our intermediate, so I can answer that question. OI with a -1 charge and HOI. And then our overall balance equation is H2O2 plus I minus, plus, and that's 2I minus, plus 2H plus. That will form I2 plus 2 waters. Okay. Now, the rate law for this reaction, if you notice, let's compare A and B because they're similar but a little bit different. A has the first step being the slow step. So when you see a problem like this where it's broken apart into the slow step and then your fast steps, what you're going to do is you're going to just write the rate law based on that. So rate equals K H2O2. How many H2O2s do I have in that slow step? Just one, so it'll be to the first power. And then I minus, how many do I have in the first step? Just one. And so then I'm going to compare it. And when the first step is a slow step, you don't technically have to do this, but it will feed into what we do in B, is H2O2 is not an intermediate, and I2, or I minus 1, excuse me, is not an intermediate, so this checks out, and this is the rate law. In B, the overall balance equation is 2NO plus Cl2 goes to 2NoCl, and our intermediate, of course, is NoCl2. But what makes this one different is when we write the rate law for the slow step, that's where the rate law comes from, we get NoCl2 times NO, and so what we need to do is see if we have an intermediate. NO is not an intermediate, so we're good. And then NoCl2 is not in my overall reaction, so it must be an intermediate. So what I need to do is I need to look at the previous step, and that's this step 1. And I could say NoCl2 to the first power is equal to NO to the first power, Cl2 to the first power, and all I need to do is just substitute. So I'm going to erase this down here. That was equal to NoCl2. And so now what I'm going to do is I'm just going to substitute it down there. And then to make it just a little bit more clean, I can make it rate equals K NO squared Cl2 to the first power.